Welcome back to the Deep Dive. Today we're plunging into one of the most critical questions facing artificial intelligence right now. How do we take the astonishing capabilities we see in models like large language models, their ability to write, to code, to reason, and make them even better?
Yeah, it's a huge question.
And it's easy to assume the answer is just throw more computers at the problem. But as this deep dive will show, the science is far more intricate and, frankly, much more fascinating.
Absolutely. There's a deep underlying science that governs how model performance behaves as we increase the fundamental resources we feed into them. The size of the model itself, the sheer volume of data it learns from, and the raw computational power used for training.
Right.
These governing principles are what researchers in the field call scaling laws.
Scaling laws. And understanding these scaling laws is our mission today. We've gathered a stack of cutting-edge research papers that explore these precise relationships, foundational studies that changed our understanding, surprising discoveries about other factors at play, and even a look at how these theoretical ideas are put into practice when building state-of-the-art AI.
Exactly. We're going to try and unpack what they tell us. By the end of this deep dive, you'll have a much clearer handle on the fundamental forces that dictate how AI models improve with scale, why certain development choices are made, and what it really means to push the frontier of these systems.
Okay, let's unpack this by starting with the bedrock ideas. What did we first think about scaling, and how has that understanding evolved?
Right. So, for a time, the conventional wisdom, and this was heavily influenced by influential earlier work like the Kaplan et al. Paper from
Right.
2020.
I remember that one.
Yeah, it tended to emphasize model size specifically, the number of parameters, often denoted by n as the primary knob to turn for performance gains, assuming you had a fixed compute budget.
So if you had a certain amount of computational power available, the thinking was build the largest model you could possibly fit within that compute constraint.
Yeah.
Bigger was better, almost exclusively through model size.
That was indeed the initial dominant view. Seems intuitive, right?
Yeah.
But then our first key source, paper 2203.15556, published by DeepMind researchers, presented a considerably different perspective.
Okay.
And it's one that has become really central to how large models are built today. Their core finding was revolutionary, actually. For optimal performance at a given computational cost, or C, you don't just maximize model size.
Right.
Instead, you must scale both model size N and the amount of training data to D in roughly equal proportions.
Okay, so it's a critical balance, not just making the model wider or deeper or just feeding it more data. It's both together. This sounds like a major shift in thinking. How did they arrive at this conclusion? It seems to contradict that earlier emphasis on just model size.
Well, it wasn't just a theoretical leap. It was grounded in an absolutely massive empirical effort. To really probe these relationships, they trained an unprecedented number of models, over 400 distinct models in total.
400 models.
Wow.
Yeah.
And these models varied significantly in size, ranging from quite small, under 70 million parameters, all the way up to models exceeding 16 billion parameters.
Huge range.
And critically, they exposed these models to vast and varied amounts of data, anywhere from 5 billion tokens up to a staggering 400 billion tokens. And they systematically altered the training duration for each specific combination of model size and data quantity.
Training 400 plus models on varying scales of data just to understand this relationship. That's an enormous investment of compute just for research itself.
It truly is. It really speaks to the fundamental nature of the question they were trying to answer. They used several sophisticated experimental approaches to analyze the results of this huge training run and identify the underlying scaling laws. So one core method, which they called Approach 1, involved fixing the model sizes at different points, say 1 billion parameters, 10 billion, etc., and then training versions of each model size on varying amounts of training tokens.
Right.
So for that 1 billion parameter model, they'd train it on like 10 billion tokens, then 20 billion, 40 billion, and so on across different training horizons, as they called them.
Okay, systematically varying the data for different fixed model sizes.
Mm-hmm.
What did that specific approach show them?
Well, by collecting the training loss curves for all these configurations, how well the model was doing at predicting the next token over time, they could then smooth and interpolate these curves.
Right.
This allowed them to figure out, for any given amount of computational effort spent during training measured in FLOPs, floating point operations, the standard unit.
Yeah, the compute budget.
Exactly. For any given FLOP budget, which combination of model size and data resulted in the lowest possible training loss? And lower loss generally means better performance on actual tasks later on.
So they could effectively say, if I have X trillion FLOPs to spend on training, The best way to spend it is with a model of size n and training data d. And how did that optimal n and d change as the compute budget increased?
Precisely. And analyzing how the optimal model size, what they called NOPT, and the optimal amount of data, DOPT, evolved as the total compute budget C increased, revealed these clear power law relationships.
Power laws, okay.
They found that NOPT was proportional to C raised to some power, let's call it A, and similarly, DOPT was proportional to C raised to another power, B.
Right.
And empirically, across their huge data set, they found that these exponents, A and B, were remarkably close. Both were approximately in their 0.50.
So NOPT scales roughly with the square root of compute. And DOCT also scales roughly with the square root of compute. This means if you have, say, 4 times the compute budget, the most efficient way to spend it isn't to just quadruple your model size on the same amount of data. No, you should roughly double your model size and roughly double the amount of data you train on. That's a significant redistribution of resources compared to the older way of thinking.
It fundamentally changed the resource allocation strategy for training. Now, another approach they used, which is kind of conceptually linked to understanding where the training loss actually comes from,
Okay.
was to fit a parametric function to model the loss, let's call it L, as a function of both model size n and data quantity d. They proposed a specific form for this function. L n d is approximately E plus ANI plus BD.
Whoa, okay, let's break down that formula. What does each piece represent there?
Certainly. Think of it this way. The E term represents what they called the irreducible loss.
The irreducible loss.
Yeah, it's like a theoretical floor. The absolute best loss you could ever hope to achieve. It's kind of like the inherent entropy or unpredictability within the natural text data itself. Even a perfect model trained infinitely couldn't get the loss below this point because language just isn't perfectly predictable.
Right, there's always some inherent randomness or ambiguity. Makes sense. What about the other terms?
Okay, the A now term. This represents the loss that occurs because the model has limited capacity. A smaller model, lower n, simply cannot fully capture the vast complexity of the language distribution, leading to approximation errors. This is the function approximation part of the error. As n gets bigger, this error term shrinks.
So error from the model just not being big enough.
Exactly. And the third term, BID, represents the loss due to not having trained the model perfectly to convergence on the full data distribution. With a finite amount of data, D, and a finite number of training steps, the model doesn't learn everything it possibly could have from the data it saw. This is essentially the optimization suboptimality term. As D increases, or you train for longer on that data, this error term decreases.
Okay, so total loss is the best possible loss, plus error from the model being too small, plus error from not having enough data or enough training time. And by fitting this formula to their actual experimental results, what did that show?
Yeah, exactly. Fitting this parametric function to their empirical data also yielded predictions for optimal scaling that were entirely consistent with the power law findings from their first approach.
Wow.
It really reinforced the core idea. To minimize the total loss for a given computational budget C, you have to increase both N and D in roughly equal proportion. It wasn't just one or the other.
So whether they looked at it from plotting the raw empirical scaling curves or by modeling the different theoretical components of loss, they landed on the same fundamental conclusion. That's pretty convincing.
They did, yeah. Across 3 different methodologies presented in the paper, they reached the same core finding. Optimal scaling requires balancing increases in both model size and training data quantity.
Okay.
And they also went a step further and demonstrated that this finding held up not just on their primary large text corpus, but also on different data sets, like the C4 text dataset, and even a dataset specifically composed of GitHub code. They detailed those results in the appendix.
So it wasn't just an artifact of one specific data set.
Exactly. It suggests that the principle was pretty general across diverse text-like data.
That's a really robust finding based on just a massive amount of empirical evidence. But, the real test for these kinds of theoretical ideas comes when you actually try to apply them to building the massive state-of-the-art models that people actually use day to day. Did they, or maybe someone else, test this out on a truly large scale?
They absolutely did, and that's where the now famous chinchilla model comes in. Chinchilla wasn't just another large language model dropped onto the scene.
Right.
It was specifically conceived and built as an empirical validation of this new scaling hypothesis. The key constraint, the really interesting part, was that chinchilla was trained using the exact same total compute budget as the earlier Gopher model.
Gopher. That was one of the big ones at the time, right? How big was Gopher?
Yeah, Gopher was huge. It was one of the leading large models, weighing in at 280 billion parameters,
Wow.
and it was trained on around 300 billion tokens.
Okay, 280 billion parameters, 300 billion tokens. So Gopher was built more in line with that older paradigm. Use your compute budget primarily to maximize the model size, N.
Precisely. Maximize N for your given C. Chinchilla, however, deliberately followed the prediction derived from these new scaling laws. For that same fixed compute budget, instead of building a 280 billion parameter model,
They built something smaller.
much smaller, they opted for a 70 billion parameter model. But, and this is the crucial part, they then trained it for substantially longer on a vastly larger data set, 1.4 trillion tokens.
Whoa! So 70 billion parameters, but 1.4 trillion tokens, compared to Gopher's 280 billion parameters and 300 billion tokens. Same total compute, same FLOPs, but radically reallocated away from just maximizing N and instead significantly increasing D relative to N.
Exactly. Same energy budget, but spent very differently based on the new theory.
Okay, the crucial question then. What happened when they put Chinchilla head-to-head against the much larger Gopher model?
The results were quite dramatic, actually, and they strongly validated the new scaling laws. Chinchilla achieved markedly better performance across the vast majority of tasks they evaluated compared to Gopher.
Even though it was 4 times smaller in parameter count.
Even though it was 4 times smaller, it was quite a stunning result at the time.
Give us some of the specific performance differences mentioned in the paper. Where did Chinchilla really shine?
The improvements were significant and really widespread. For instance, on the Lambda task, that's one that tests the ability to predict the final word of a sentence, often requiring pretty broad context.
Tricky one.
Chinchilla scored 77.4% accuracy compared to Gopher's 74.5%. On reading comprehension benchmarks like Race High and Race Middle School, Chinchilla saw really striking improvements, achieving over 10% higher accuracy on both compared to Gopher.
Over 10%. That's huge in benchmark terms.
It really is. And in closed book question answering, like on the natural questions dataset, Chinchilla set new state-of-the-art results at the time. It reached 31.5% accuracy with just 5 examples provided, that's 5 shot, and 35.5% with 64 examples, 64 shot. That substantially outperformed Gopher's 21% and 28% respectively. It also substantially beat Gopher on Trivia QA.
Wow, those aren't minor differences at all. Big jumps on reading comprehension, big jumps on QA. What about broader benchmarks?
Right. The trend held even on the extensive Big Bench suite, which contains a whole load of challenging AI tasks. Chinchilla outperformed Gopher on nearly every single task in that suite. It only trailed on 4 specific ones identified in the paper: college mathematics, econometrics, moral scenarios, and formal logic.
So outperforming on almost everything except a few very specific, maybe niche areas.
Pretty much. And if you look at the relative improvement figures they plotted in the paper, Chinchilla showed over 100% relative improvement compared to Gopher on tasks like identifying the odd one out in a set, tackling analogical similarity questions, GRE reading comprehension tasks, and certain Boolean metaphor tasks.
100% relative improvement on some tasks. That level of consistent improvement across so many diverse tasks is just a powerful empirical endorsement, isn't it? It seems to unequivocally show that for a fixed compute budget, you are much better off training a model that is only 70 billion parameters on 1.4 trillion tokens compared to training a massive 280 billion parameter model on only 300 billion tokens.
It absolutely solidified the principle. The Chinchilla paper was a real landmark that significantly shifted industry practice towards training compute optimal models rather than just the largest possible models.
Right.
Now, while their primary focus was clearly on this interplay between model size N and data quantity D, the authors did acknowledge that other hyperparameters are crucial too, of course. Things like learning rate, batch size, architectural specifics like the width-to-depth ratio of the transformer layers.
Yeah, all the other knobs you have to tune.
Exactly. They mentioned relying on existing work for optimizing many of those, though they did note an interesting detail. They chose slightly less deep models than some prior recommendations suggested, finding this actually offered better wall clock trading speed on their particular hardware setup, even if it wasn't theoretically optimal depth according to some formula. Practicality matters.
That's a good point. Theory meets reality. Did their study touch on any potential societal implications of scaling, like issues around bias or toxicity?
They did briefly evaluate chinchilla on metrics related to gender bias using the Winnow gender data set, and also on its propensity for generating toxic language. Their findings in this area were pretty consistent with earlier work, particularly the analysis done on the gopher model.
And what was that finding?
It basically indicated that simply scaling up the core model parameters, making n bigger or training longer on more data D, did not seem to have a significant effect on the rate of unprompted toxic language generation.
So making the model smarter, in the conventional sense, didn't automatically make it safer or less biased.
That seemed to be the conclusion. It suggested that addressing these really important safety and fairness concerns requires specific techniques beyond just optimizing the core scaling of N and D during pre-training. It needs dedicated effort, different methods.
Okay, so the foundational insight is crystal clear. Balance model size and data when scaling your training compute budget. That's the chinchilla principle. But AI progress isn't just about training ever larger models using more FLOPs, right? What about improvements that aren't just about raw scale?
Exactly. And this leads us really nicely into the next section, looking beyond just raw pre-training scale to the critical roles of, well, algorithmic progress and also efficiency during inference time. Scaling up N&D is a massive factor, absolutely, but it's only one part of the story of how these AI models actually get better over time.
You mean like developing smarter ways for the model to learn in the first place, or maybe better architectural designs that are just inherently more efficient?
Precisely that. Our second source, paper 2403.05812, specifically investigates this exact question. These researchers set out to try and disentangle the contributions to performance gains. How much comes from simply scaling up physical resources, more compute, more data, versus how much comes from fundamental improvements in the algorithms themselves?
Wow, that sounds incredibly challenging to pull apart. I mean, these things often happen together, right? Better algorithms might enable bigger scale. How did they even manage to quantify that separation?
Yeah, it's super tricky. They used a pretty sophisticated statistical model. It was inspired by the very neural scaling laws we've just been discussing, modeling performance as a function of scale. But they combined this with a technique called Shapley values.
Shapley values. Isn't that from game theory?
Exactly, yeah. Borrowed from cooperative game theory. Shapley values provide a principled way to fairly attribute the contribution of each player, in this case, different factors like compute scale, data scale, and algorithmic progress to the overall game, which here is the improvement in model performance observed over time.
Okay, so they're using game theory math to fairly divide the credit for AI getting better over the years among compute, data, and algorithms. That's clever. What did their analysis actually show about the role of algorithms in all this?
Well, their finding was quite surprising and I think pretty powerful. They concluded that algorithmic improvements explain a very significant portion of the observed performance gains over the years. They estimated it to be somewhere between 25% and 70%.
25 to 70%. It's a huge range, but even the low end is substantial.
It is, and critically, they found that the contribution from algorithmic advances was roughly equal to the contribution from scaling up physical compute resources, which they estimated accounted for 30% to 55% of the gains. Data scaling was also important, contributing maybe 10% to 30%.
Wait, so algorithms are pulling roughly as much weight as just throwing more hardware at the problem. That really challenges the common narrative that AI progress is only about scale, doesn't it?
It absolutely does. It suggests smart ideas are just as important as big iron. And they characterized the nature of this algorithmic progress as largely compute augmenting.
Compute augmenting. What does that mean exactly?
What it means is that these algorithmic advances make more efficient use of the compute that's available. They actually estimated that this type of algorithmic progress effectively halves the physical compute required to achieve a specific performance level approximately every 9 months.
Having the compute needed every 9 months. That's an incredibly rapid pace. That's significantly faster than hardware improvements like Moore's Law, right? Moore's Law is usually talked about on an 18-24-month timescale for doubling density.
Exactly. It highlights that innovation on the algorithmic side might actually be an even more potent driver of progress than just the raw increase in hardware capability, which is often what gets the headlines.
That's a profound thought. Can you give an example of this kind of compute augmenting algorithmic progress?
Well, think about a major architectural breakthrough.
Like the transformer architecture itself, the thing that powers almost all modern LLMs.
Exactly like the transformer. The paper estimates that the efficiency gain introduced by the transformer architecture compared to the recurrent neural networks or LSTMs that largely preceded it for sequence modeling,
Yeah, the older stuff.
that gain is equivalent to using around 7.2 times the compute. Just switching architectures was like getting 7x more hardware for free, in a sense.
Well,
And this single architectural shift represents about 20% of the total algorithmic gains they measured over the 9 years covered in their data set. That's almost 2 full years of that rapid 9-month compute having progress just from that one invention.
why was the transformer such a huge algorithmic leap, specifically in terms of compute efficiency? What made it so much better for hardware?
Well, the paper doesn't delve into the exact reasons deeply, but a widely accepted view in the community is that the transformer's core mechanism, the self-attention layer, is inherently much more parallelizable than the sequential processing required by LSTMs or RNNs. LSTMs have to process tokens one after another, creating a bottleneck. Attention can look at all tokens simultaneously, in parallel.
Ah, so it maps much better onto modern parallel computing hardware like GPUs and TPUs.
Precisely. It makes it vastly more efficient to train on the kind of hardware we have now. So it wasn't just a perhaps cleverer way to model sequences in theory, it was an algorithm fundamentally better suited to exploiting the trends in computing hardware.
That makes a lot of sense. It's an algorithm that unlocks the potential of the hardware. Now, the authors of this kind of historical analysis must face some limitations, surely. Trying to untangle all these factors over years of research seems incredibly difficult.
Oh, absolutely. And they are very upfront about the challenges in the paper. For one, the data on older models, especially from before 2017 or so, is much more sparse, which makes the analysis less certain in the early years. It's also inherently difficult to perfectly separate factors that are often correlated. For example, new algorithms are frequently introduced alongside increased scaling efforts. Was it the algorithm or the scale that caused the jump? Hard to say definitively sometimes.
Yeah, they often come as a package deal.
Exactly. Plus, there are inconsistencies in training and evaluation procedures across different research papers over the years. Think about variations in how text is tokenized, different data preprocessing steps, or even techniques applied during runtime adaptation like fine-tuning. All these can muddy the waters when comparing performance across time.
Yeah, it's tough to ensure you're always comparing apples to apples across a decade of rapidly evolving research practices.
Precisely. They specifically note, for example, that the increasing context length used in models over time, the amount of text they can look back at, could potentially account for a significant portion, maybe 10% to 60%, of the yearly loss reductions they attributed purely to algorithms. Longer context is arguably an algorithmic improvement in how the model processes input, but it's also tied closely to architecture and compute scaling.
That's a good point.
Also, their analysis struggles to distinguish between improvements in data quality over time. Maybe we just got better at cleaning data and improvements in how efficiently algorithms use the data they're given. Both would appear in their model as needing less data for a given performance level.
Okay, fair points about the inherent complexities and caveats of this kind of analysis, but the core insight still seems really powerful. Algorithmic progress, making compute more efficient, is a major, maybe often underappreciated engine of AI improvement.
Yeah.
And it's running at a pace that potentially even outstrips hardware gains.
I think that's the key takeaway, yeah.
Okay, so once a model is trained, maybe it's a very large model trained according to those ND scaling laws we talked about. How do we get the best possible performance out of it for a specific task when we're facing a constraint not on training compute, but on the compute available when we actually use the model at inference time?
That's a great transition, because that brings us to our third source, paper 2408.000724, which zeroes in on exactly this challenge of inference scaling. This is a completely distinct problem from training scaling.
Right.
The question here is, okay, you've got your trained model, maybe several models of different sizes, and you have a fixed compute budget specifically for inference for generating the model's output for each user query. How do you choose the optimal model size and the optimal inference strategy to maximize accuracy on a particular task, given that budget?
And inference strategies.
Yeah.
That's more than just feeding the input and getting the output right.
Exactly. Inference strategies can range from very simple methods, like just greedily picking the single most likely next token at each step, to much more complex techniques involving generating multiple possible solutions, maybe using voting or employing sophisticated search algorithms to explore the space of possible outputs.
Okay, so let's say I've got my pre-trained models sitting there, maybe a 7 billion parameter one, a 13 billion, a 70 billion, and I know I can only spend, say, X number of FLOPs every time someone asks the model a question on my service. How do I spend those precious inference FLOPs most effectively? Should I just run the biggest model I have, the 7DB, just once using a simple decoding method? Or could I maybe run the smaller 7B model multiple times with some clever, more compute-intensive strategy?
That's the exact problem they tackle. And their key findings here are particularly impactful, I think, for anyone actually trying to deploy these models efficiently in real-world applications where inference cost is a huge factor.
Okay, what did they find?
They found that, perhaps counterintuitively, a smaller model, when combined with more sophisticated inference strategies that involve generating more tokens or exploring multiple candidate solutions, can frequently outperform a larger model that is forced to operate under the same inference compute budget, but using a simpler, less compute-intensive strategy, like simple greedy decoding.
Wait, hang on. So you're saying a 7 billion parameter model running with some smart search algorithm could actually be more accurate on a task than a 70 billion parameter model just doing a basic single pass decoding, even if they use the exact same total inference FLOPs per query.
Their experiments strongly suggest this is often the case, yes. The core insight is that your inference compute budget isn't just for pushing the input through the model's parameters once. You can spend that budget on more sophisticated processing of the model's outputs or its intermediate thinking steps. And doing that intelligently with a smaller, faster model can be more effective overall than just running a larger, slower model straightforwardly.
That's a really significant realization for anyone trying to serve these models at scale. Inference compute is often the dominant operational cost.
It absolutely is. And they also demonstrated a limitation of the simpler, more common approaches. Strategies based purely on sampling, like generating several different answers and taking a majority vote, they found that these eventually hit a performance ceiling as you increase the inference compute by taking more and more samples.
So just sampling more doesn't keep improving things indefinitely.
Right. It shows that just throwing more inference compute at basic sampling strategies isn't always enough. You eventually need more advanced inference algorithms to break through certain performance limits for a given model size.
Okay, so advanced inference algorithms are key to maximizing performance per inference, FLOP. What kind of algorithm did they propose or investigate?
They introduced a novel algorithm they call rebase. It stands for Reward Balanced Search.
Rebase.
And as the name suggests, it's a tree search method. Tree search algorithms essentially explore different possible sequences of tokens, branching out like a tree of possibilities, trying to find the best overall path or final answer.
A bit like the kind of search algorithms used in game-playing AI, like chess or Go, for example, exploring different move sequences.
Conceptually similar, yes. Definitely inspired by those ideas from AI planning and search, but adapted specifically for the sequential nature of language generation and reasoning tasks.
Okay. What's special about Rebase compared to other search methods?
A key advantage of Rebase, according to the paper, is how it guides its search through this tree of possibilities. It uses a reward model, which is often a separate, smaller model, trained specifically to estimate the quality or correctness of a potential answer, or even an intermediate sequence of tokens.
Right, like a judge.
Exactly, like a fast, cheap judge. It uses this reward model to steer the search towards promising branches and to evaluate the quality of intermediate steps without needing to perform full, computationally expensive rollouts. Rollouts are often used in other methods like Monte Carlo tree search, MCTS, where you simulate potential outcomes all the way to the end to estimate the value of a current state. Rebase tries to avoid that expensive simulation.
So it's a potentially smarter, more efficient way to explore the possible outputs during inference compared to brute force simulation or simple sampling. How did Rebase actually perform in their tests?
They found Rebase to be Pareto optimal across the inference compute budgets they tested.
Pareto optimal. What does that mean in this context?
It means it achieved a better trade-off between accuracy and inference compute cost than the alternative strategies they compared it against, including the simple sampling voting methods and even the more complex MCTS. Essentially, for any given inference compute budget, Rebase delivered higher accuracy, or alternatively, it could achieve the same accuracy as the other methods, but using less inference compute.
Getting more performance out of the same computational effort during inference, or the same performance for less effort, that's a huge practical win for deployment.
It really is. And importantly, they didn't just test this on one model. They ran experiments across different model families. They mentioned Pythia, Mistral, Lemma, and on demanding mathematical reasoning benchmarks like GSM-8K and MAT 500.
So it wasn't just a quirk of one particular model.
Exactly. It demonstrated that the findings weren't confined to a single model architecture, but seemed to highlight a more general principle about how to effectively spend your inference compute budget by combining model size and algorithmic sophistication.
Okay, so the overall picture is getting much more nuanced now. We've got scaling training, which means balancing N and D according to compute. We've got algorithmic progress, which is constantly making that compute more efficient, maybe even outpacing hardware. And we've got scaling inference, which involves not just picking a big model, but smartly combining model size with clever algorithms like rebase to maximize accuracy per FLOP. Now, how do these different principles actually play out when a major AI lab sets out to build a new state-of-the-art model in the real world?
That's the perfect question, and it leads us straight to our fourth source, paper 2407.21783. This paper provides a really detailed look at the development of the Llama 3 family of models by Meta AI.
Ah, Llama 3, one of the current top open models.
Exactly, and it serves as an excellent case study because the paper explicitly states how their understanding of scaling laws, and they directly cite both the foundational Kaplan paper and the crucial follow-up Hoffman Chinchilla work we just discussed, profoundly influenced their design choices and their entire development process.
So they weren't just building a model blind. They were consciously trying to apply the science of scaling as they understood it at the time.
Precisely. For example, they note that their largest model, the Llama 3 405B, 405 billion parameters.
Huge.
Huge.
Right.
But it's actually smaller in parameter count than some earlier, less performant models like Google's Pay-LM, which was
Right.
540 billion parameters.
Right.
But by adhering to the insights from scaling laws, specifically that chinchilla principle about balancing N and D, and by allocating a truly immense pre-training compute budget, they mentioned it was almost 50 times the budget used for the previous Llama 270B model.
50 times the compute.
Yeah. By spending that massive budget, not just on maximizing size, but on training for longer on a huge data set relative to the model size, they achieved significantly better results with Llama 3 405B compared to those earlier, larger models. They spent that budget according to the N and D square root scaling.
So they really took the N proportional to C to the 0.5, D proportional to C to the 0.5, finding the heart. Applying 50 times the compute meant a much larger model and vastly more data trained for longer.
Exactly right. The Llama 3 development process, as they describe it, can broadly be seen in two main stages. There's the pre-training stage, where the model learns the fundamental structure of language and general world knowledge from that vast text corpus. And then there's the post-training stage, where it's further refined, aligned with human feedback, and enhanced with specific capabilities like following instructions or safety. And scaling was a fundamental challenge and consideration throughout both of these stages.
Okay, let's dive into that. How did data scaling, for instance, manifest in the Llama 3 project? We know they needed a lot more data for that 405B model.
The scale is almost hard to grasp, honestly. For the largest 405B model, they used a massive multilingual corpus totaling 15.6 trillion tokens for pre-training.
15.6 trillion tokens. That's astronomical.
It really is. But as the scaling laws suggest, and as they emphasize, it's not just about raw quantity. Quality and diversity are absolutely paramount at the scale. They implemented extensive data cleaning and deduplication methods. And not just basic stuff like removing duplicate web pages or documents. They did deduplication even at the line level within documents.
Line-level deduplication across 15 trillion tokens. That sounds computationally intense just for data prep.
It absolutely highlights the level of engineering effort required when you're scaling data to this magnitude. They acknowledge that line-level deduplication could sometimes remove even high-quality text if it happened to be very common, like standard code comments or boilerplate, but their empirical findings showed that overall this aggressive deduplication led to performance improvements.
Interesting trade-off. Quality over quantity, even removing some good stuff if it's too repetitive.
Seems so. They also carefully composed their data mix. It wasn't just web text. They incorporated a blend of general web data, mathematical content, code repositories, and multilingual data. They give rough percentages, about 50% general, 25% math, 17% code, and 8% multilingual in the final mix for the 405B.
Okay, a diverse diet.
And they used a specific technique towards the very end of pre-training called annealing. This involved reducing the learning rate significantly and train for a short period on relatively small amounts of very high-quality data. They found this gave a noticeable boost to performance on key evaluation benchmarks.
So scaling data effectively means not just more, but cleaner, more diverse, and strategically applied data, maybe even with special high-quality injections at the end. What about the infrastructure side? Training a 405 billion parameter model on 15 trillion tokens must require incredible hardware.
The infrastructure requirements are just staggering. They trained on a cluster utilizing 24,000 GPUs. 24,000.
Oh.
And these GPUs weren't just sitting there. They were connected via a complex, three-layer, close network topology. Training models at this scale involves absolutely massive communication between GPUs, especially for exchanging information during the various parallel processing steps needed to fit the model and data.
Right, the GPUs need to talk to each other constantly.
Exactly. So, to handle this communication efficiently, they heavily optimize their parallelism strategies and their job scheduling software to be what they call network topology aware.
Network topology-aware scheduling, what exactly does that entail in practice?
It basically means designing the system to minimize communication across the parts of the network that have higher oversubscription ratios.
Oversubscription ratio, that sounds like jargon.
It kind of is, but the idea is simple. An oversubscription ratio tells you how much potential traffic a part of the network could theoretically handle versus its actual capacity. A ratio of 1.1 means you have dedicated bandwidth. A higher ratio, like 1.7, which they mention for their aggregation layer, means multiple connections might end up competing for the same limited bandwidth, creating potential bottlenecks.
Ah, okay. So you want to avoid sending lots of traffic through the highly oversubscribed parts if you can.
Precisely. By making the scheduling system aware of the network map, they could design communication patterns to keep traffic within the lower oversubscribed layers of the network as much as possible, avoiding congestion on those critical links. They also use techniques like load balancing by creating multiple distinct network flows. They mentioned 16 separate flows per pair of GPUs to distribute the communication load more evenly across the available paths.
So it's not just about having tens of thousands of GPUs, it's about the intricate details of the network connecting them and deeply optimizing how the training software actually uses that network fabric.
Yeah.
That sounds like an incredible systems engineering challenge that scaling introduces.
It absolutely is. And even with the best engineering, at that scale, failures are just an inherent part of the process. You can't avoid them. The paper gives some fascinating, if slightly alarming, statistics on this.
Oh, yeah.
During a 54-day snapshot of the pre-training run for the largest 405B model, they experienced 466 job interruptions.
466 interruptions in less than 2 months. That sounds incredibly unstable. How did they ever manage to complete the training run?
This is where the resilience of their system engineering was absolutely crucial. Despite that high frequency of failures, and they know almost 80% were unexpected, with over half attributed to GPU hardware or suspected hardware issues.
Mostly hardware failures.
Mostly hardware, yeah. But their automated fault tolerance mechanisms handled the vast majority of these interruptions seamlessly. The system could detect the failure, checkpoint the state, restart the job, often on spare hardware, without human intervention. They state that significant manual intervention was required only 3 times during that entire 54-day period, despite hundreds of failures.
Wow. That really underscores that scaling training isn't just about raw compute power. It's about building these incredibly robust, highly automated systems that can just absorb and recover quickly from frequent hardware and software failures. Resilience at scale.
Exactly. Resilience engineering is paramount.
Okay, that's mind-boggling on the pre-training side. Beyond that core training, how did these scaling principles apply to the post-training phase, the fine-tuning, the alignment with human preferences?
Post-training also scaled dramatically for Llama 3. They talk about utilizing millions of human instructions and preference judgments to align the model.
Millions of human data points.
Yeah. They employed a combination of standard and advanced techniques. Things like rejection sampling, where they generate multiple possible responses from the model for a given prompt, and then use a separate, smaller reward model trained on human preferences to automatically select the best one among the candidates.
Okay.
They used supervised fine-tuning, SFT, learning to mimic high-quality responses. This used data annotated by humans, but also, crucially, synthetic data generated by earlier, less capable versions of Llama 3 itself.
Ah, the model helping to train his future self again. That's a fascinating feedback loop powered by scale. What kind of synthetic data did they generate? This seems like a key scaling technique.
It really does seem key. They generated synthetic data tailored to improve specific capabilities that are critical for making an AI helpful and reliable. For instance, they generated data for programming language translation, specifically focusing on improving the model's ability to translate between common languages and less common ones where human data is scarce.
Smart. Using the model to bootstrap data for the long tail.
Exactly. For complex mathematical and reasoning problems, they generated step-by-step reasoning traces, essentially showing the model how to think through the problem. And they used techniques like self-verification, where the model tries to check its own reasoning steps and reward models to ensure the correctness and quality of these generated steps. They even mention employing methods inspired by MCTS, that search algorithm, within this synthetic data generation process for the really hard problems.
Wow, using search to generate better training data? That's meta.
It is. They also generated data specifically for long context tasks, like question answering over lengthy documents or summarizing long texts. And they generated data to teach the model how to use external tools, covering scenarios from single-step tool use to multi-step interactions, and even interactions involving file uploads.
So they're systematically leveraging the model's own nascent capabilities to generate more diverse and targeted training material, effectively scaling the data generation process itself. It's like scaling innovation.
Yeah.
They also mentioned adding multimodal capabilities to Llama 3, right? Images, video, speech. How did scaling factor in there?
Yes, and their approach to adding these multimodal capabilities, image, video, and speech understanding and generation, also reflects a strategy informed by scaling considerations, though it was different from just trying to build one giant multimodal model from scratch. They use what they call a compositional approach.
Compositional approach. What does that mean in this context? How is it different?
It means instead of trying to pre-train the entire massive language model simultaneously with text and image and video and speech data, which would be incredibly complex and computationally expensive,
Yeah, sounds nightmarish.
they instead trained separate specialized encoders and adapters for each modality. So one module for processing images, another for video, another for speech. And then they integrated these specialized modules with the powerful pre-existing Llama 3 language model.
Okay, so it's more like building specialized sensor modules in eye and ear, and then plugging them into the core language processing brain.
That's a pretty good analogy, yeah. For images, they used a large vision transformer, VIT encoder, around 850 million parameters itself, trained on a massive 2.5 billion image text pairs. This encoder extracts meaningful features from images, and these features are then fed into the main language model via some adapter layers. Importantly, they didn't freeze the image encoder parameters during this integration, they let them adapt.
Okay, and for video and speech, similar idea.
Similar idea with modality-specific tweaks. For video, they actually started with the pre-trained image model weights, which makes sense as video builds on images. Then they added video-specific layers, like temporal aggregators and cross-attention mechanisms to handle the time dimension. Crucially, during this video adaptation phase, they froze most of the parameters from the image model and the LLM, and trained only these new video-specific parts. They processed videos by sampling frames, like 16 frames per clip, and using an aggregator.
So more efficient fine-tuning just for the video parts. Makes sense. And speech.
For speech, they first pre-trained a separate speech encoder on a huge dataset, 15 million hours of unlabeled speech data. They were careful here, using voice activity detection, VAD, to filter out silence and filtering out personally identifiable information, PII. This encoder learns general acoustic patterns. Then, this pre-trained speech encoder was connected to the LLM and fine-tuned on specific supervised tasks like speech recognition, translation, and even generating dialogue responses directly from speech input.
That compositional strategy seems like a more modular, perhaps more resource-efficient way to add diverse capabilities rather than trying to scale everything up together in one monolithic model. How did this approach actually perform in their evaluations?
The results reported in the paper were quite impressive. This compositional approach yielded performance that was competitive and in many cases apparently even better on various multimodal benchmarks compared to models that had undergone native multimodal pre-training right from the start.
Really? Better than models trained multimodally from scratch?
In some cases, yes. They reported particularly strong results on video understanding tasks like perception test. And they demonstrated state-of-the-art results on speech recognition benchmarks, even outperforming established specialized models like OpenAI's Whisper and Meta's own Seamless M4T in their head-to-head evaluations.
Wow.
They even leveraged the Llama 3 language model's understanding, accessed via its embeddings, for subtasks within speech generation, like text normalization and prosody modeling, to improve the quality of synthesized speech. It really suggests that scaling via this kind of modular composition can be a very effective and perhaps more efficient strategy.
So scaling insights inform not just the core model training, N versus SD, but also how you architecturally add new modalities and capabilities efficiently. Fascinating. Now, we talked earlier about the importance of inference scaling, separate from training scaling. How did Llama 3 specifically apply ideas to make inference efficient, especially for their massive 405 billion parameter model?
Right. Running inference on a 405B model is a huge challenge in itself. Just loading the model's weights into GPU memory is non-trivial. They addressed this using a couple of key techniques mentioned in the paper. One was pipeline parallelism.
Pipeline parallelism.
Yeah, this involves splitting the model's layers across multiple GPUs. So the input goes through the layers on the first GPU, the intermediate activations are passed to the second GPU for the next set of layers, and so on. This is essential just to fit the massive BF16 16-bit brain float version of the model across available hardware.
Okay, so pipelining to distribute the model. What else?
They also heavily leveraged FP8 quantization.
FPA quantization, right? Says using lower precision numbers, 8-bit floating point for the calculations instead of 16-bit or 32-bit.
Exactly. Using 8-bit precision significantly reduces the memory footprint needed to store the model weights, and also speeds up the computations, as matrix multiplications are faster with lower precision. They applied this FP8 quantization to roughly 50% of the compute within the feed-forward layers of the transformer blocks. Those are typically the most computationally intensive part during inference.
So half the math gets done faster and with less memory.
Pretty much. Leveraging this effectively required specific hardware support, like that available in NVIDIA's H100 GPUs, which have specialized units for fast FP8 math. They also noted that implementing this required careful handling using dynamic scaling factors and making some quality adjustments because the model's performance was somewhat sensitive to this drop in precision. But it's a critical scaling technique for making these gigantic models practical enough for deployment.
It's just mind-boggling, the sheer number of layers of optimization needed across data, infrastructure, training algorithms, parallelism, post-training techniques, and now inference quantization, just to make these scaled-up models work effectively and efficiently.
It really is a testament to the incredible engineering involved. And finally, the Llama 3 paper discussed how scaling impacted their approach to safety. This wasn't treated as just an afterthought or a final filter, but something incorporated end-to-end throughout the development lifecycle.
Okay, how did scaling influence their approach to making the model safe and reliable?
Well, addressing safety effectively also involves scaling the effort. They used, again, millions of human preference judgments, but many specifically related to safety scenarios, identifying harmful content, avoiding bias, refusing dangerous instructions.
So scaling the safety data collection and annotation.
Right. And they used tailored safety tuning techniques. Things like safety SFT, supervised fine-tuning, which used human annotated data, including tricky borderline examples to teach the model better nuance around potentially sensitive topics. They also use safety DPO, direct preference optimization, learning from pairs of responses where humans indicated which one was safer or more appropriate, specifically incorporating carefully constructed mixes of adversarial examples prompts designed to trick the model into generating unsafe content alongside standard helpfulness examples.
Trying to make the model robust against attacks.
Exactly. They even mentioned using techniques involving comparing model responses that were orthogonal in their learned embedding space, meaning they represented distinctly different types of content, like safe versus unsafe, or helpful versus harmful to refine the safety alignment.
That sounds quite sophisticated. Did they find any interaction between model scale and safety? Like, are bigger models easier or harder to make safe?
That's a really interesting point they touched upon. They noted that the inherent trade-off you always face in safety tuning, the trade-off between reducing the violation rate, VR, which is how often the model generates unsafe content when it shouldn't,
Right.
and increasing the false refusal rate, FRR, which is how often the model incorrectly refuses to answer a perfectly harmless query because it's being overly cautious.
The I cannot help you with that problem.
Exactly. They found that balancing this VRFR trade-off effectively is actually more challenging for smaller models compared to larger ones.
Oh, really? Why is that?
According to their findings, achieving a desired low VR without excessively increasing the FRR requires a larger proportion of safety-specific training data relative to general helpfulness data when you're working with smaller models. The bigger models seem slightly better at handling the nuance required for safety alignment with less targeted safety data.
So, larger models, while more capable overall, might also be inherently a bit better at learning the nuances needed for safety alignment. It's counterintuitive, maybe.
It suggests that making smaller models equally safe might require a disproportionately larger investment in safety-specific data and tuning compared to larger models. Of course, they also developed and deployed specific tools designed to scale safety enforcement after training. They mentioned LlamaGuard 3,
Oh my God, right.
which is used for filtering both user inputs, prompts, and the model's outputs. The paper includes results showing LlamaGuard 3 significantly reduced the violation rate across various languages, although, as expected, it did come with an increase in the false refusal rate. They also use tools like Prompt Guard for detecting prompt injection attacks, and Code Shield, which employs static analysis techniques to try and flag potentially insecure code generated by the model.
A whole suite of safety tools scaling alongside the model.
Hmm.
Did their research in the paper show any direct links between scaling the model's capabilities and potentially scaling the risks, like the model's susceptibility to misuse?
Yes, they were quite transparent about this and included empirical results testing potential vulnerabilities. They found, for instance, that while the larger Llama 3405B model generated higher quality code overall, as measured by things like BLEU score,
Yeah.
it also generated more instances of insecure code in response to certain prompts compared to the smaller 70B model.
Oh, interesting. So better code, but also potentially more bad code.
Potentially, yes. The 405B model was also found to be more susceptible to actually executing potentially malicious code if it was included directly within a user's prompt. They reported a 10.4% compliance rate on such tasks for the 405B, compared to only 3.8% for the 70B model.
Wow, that's a significant difference.
Similarly, the larger model was found to be more vulnerable to certain types of text-based prompt injection attacks designed to bypass its safety filters, with a 21.7% success rate reported for the 405B model on one specific test suite. They also tested against scenarios like generating spear phishing emails and automating parts of cybertext, finding the models could be moderately persuasive, but ultimately failed to, for example, autonomously exploit software vulnerabilities in their tests.
Those findings clearly illustrate a crucial point. Scaling capabilities and model size doesn't happen in a vacuum. It can also inadvertently scale potential risks and vulnerabilities, which necessitates equally scaled and sophisticated safety engineering efforts running in parallel.
Absolutely. It really underscores that it's a constant arms race, or maybe a coevolution, between capability, optimization, efficiency, and safety at scale.
So to wrap up the Llama 3 case study, what was their main conclusion from this massive effort?
Their paper really emphasizes that their core success came from a relentless focus on three things: extremely high quality data, immense scale in both model size and in data D following the scaling laws, and aiming for architectural simplicity where possible. They also state quite clearly their belief that substantial further improvements are still achievable beyond Llama 3.
And how did they see Llama 3 stacking up against the other big players?
They benchmarked the Llama 3405B extensively against other leading closed models like GPT-4, GPT-4, and Claude 3.5 Sonnet. They found it to be highly competitive overall, performing on par or sometimes outperforming in specific areas like multi-turn reasoning and coding compared to the original GPT-4, holding its own on English prompts versus GPT-4o, and showing strong multilingual capabilities compared to Claude 3.5 Sonnet at the time of their writing. They also acknowledged areas where it trailed, particularly in coding and reasoning benchmarks against the very latest Claude 3.5 Sonnet.
And they made a point about human evaluations too, right? That benchmarks aren't everything.
Yes, they noted that human evaluations are complex and can be influenced by subtle factors beyond just factual correctness or task completion, like the model's tone, its writing style, or the structure of its response.
Hmm.
But overall, their conclusion is that Llama 3 represents the current state of the art among openly available models, and they strongly advocate that releasing these powerful models publicly is essential for fostering responsible AI development and innovation across the entire field.
That gives us a really comprehensive picture. It shows how all these principles of scaling, from the foundational ND balance discovered by Chinchilla to the massive infrastructure and resilience engineering needed, the algorithmic progress in post-training with synthetic data, the compositional approach to multimodality, and the critical considerations around inference efficiency and safety, how they all come together in the development of one of today's most advanced models. But we started this whole deep dive by asking if these scaling laws are unique to language models. Are they? Or do these principles apply elsewhere?
That's the perfect final question, and it brings us neatly to our fifth and final source,
Mhm.
paper 2004-11.17470. This one looks at scaling laws in a completely different domain, video diffusion models.
Video diffusion models.
Okay.
So these are models used not for generating text, but for generating actual video content, like text-to-video generation.
Exactly. Models that create pixels over time, not text tokens. The researchers here ask a very similar set of fundamental questions. Do scaling laws exist for these video diffusion transformers? And if so, how can we predict the optimal model size, the expected performance, and the crucial training hyperparameters given a certain compute budget for training?
So applying the same fundamental logic about optimal resource allocation, but shifting from the domain of language to the domain of video generation. Did they find evidence of scaling laws there too?
They did. They confirmed the presence of predictable scaling laws for these video models as well. Performance improves reliably with more compute, data, and model size following mathematical relationships. However, they identified a really key difference compared to what's typically emphasized for language models like LLMs.
Oh, what was the difference?
They found that these video diffusion models are significantly more sensitive to specific training hyperparameters, particularly the learning rate and the batch size.
Ah, okay. So for LLMs, N and D are the dominant factors in the scaling laws we usually discuss. But for video diffusion, getting the learning rate and batch size just right as you scale everything else up becomes much more critical for hitting optimal performance. The sensitive knobs are different.
Exactly that. For LLMs, while hyperparameters obviously matter a lot for successful training, the dominant scaling dynamics seem well captured primarily by N and D. For video diffusion, based on this paper, successfully navigating the scaling process requires getting the learning rate and batch size precisely right in coordination with the scaling of model size, data, and compute. It means accurately modeling the scaling behavior for these video models isn't just about predicting the optimal NND for a given budget. You must also be able to predict the optimal learning rate and batch size that should go along with that NND.
That makes the prediction problem harder. You need to predict more variables simultaneously. Was their main contribution proposing a scaling law that could actually do that, predict the optimal hyperparameters alongside the optimal size and expected performance?
Yes, that was their core contribution. They proposed a new, refined form of scaling law specifically for video diffusion transformers. This law not only predicts the optimal model size and the resulting performance for a given compute budget, but it also predicts the corresponding optimal learning rate and batch size that should be used to achieve that performance.
Okay, what's the practical benefit of having a scaling law that tells you the optimal hyperparameters too, not just the optimal size? Does it lead to better models?
It leads to more efficient models, particularly during inference. They showed that by using their proposed scaling law and training models with these predicted optimal hyperparameters, they could achieve comparable final video quality performance to models trained using more conventional, maybe less precisely optimized methods, but with significantly better efficiency when it came time to actually use the model to generate videos.
Better inference efficiency, how much better?
They reported that using models trained according to their scaling law reduced the computational cost of inference by a remarkable 40.1% at a specific compute budget they tested, 1 in 10 T-flops.
Wow, a 40% reduction in inference cost just from training with more precisely predicted hyperparameters, according to a scaling law. That's massive. That could be the difference between a model being deployable or not.
It really highlights the potentially tight connection between optimizing the training process according to accurate scaling laws and the resulting efficiency of the final model at inference time. Getting the training just right can lead to a model that's fundamentally cheaper to run later.
That's a powerful connection.
And they also developed a more generalized form of their scaling relationship. This generalized version can predict performance even for non-optimal model sizes.
Why is that useful? If you know the optimal size, why predict performance for suboptimal ones?
Well, it's useful in practice because real-world deployment constraints, especially inference cost limits or latency requirements, might mean you simply can't deploy the exact model size that was theoretically optimal during training, which might be too big or slow. This generalized law allows developers to predict the performance they'd likely get from smaller, less compute-intensive models at inference time, helping them find the best possible trade-off point given their specific deployment constraints.
Okay, that makes sense. It gives you a map of the performance landscape, not just the single peak. So the big takeaway here seems to be that scaling laws are indeed a widespread phenomenon, showing up across different AI domains, not just limited to text generation.
Right.
But the specifics of those laws, particularly which parameters are the most sensitive and need the most precise modeling and co-optimization as you scale, can vary significantly depending on the model architecture, transformer versus fusion,
Yeah.
and the nature of the task, generating text versus generating video.
Precisely. The core underlying idea of optimal resource allocation under computational constraints seems to hold true broadly, but the specific mathematical formulas and the critical variables you need to track are likely domain-specific.
We've certainly covered a huge amount of ground today, diving really deep into the science that sits beneath the surface of today's incredibly powerful AI models.
Yeah, we really went from the foundations up. We started with that fundamental shift in understanding, realizing that optimal scaling during training isn't just about building the biggest possible model, maximizing N, but about carefully balancing model size, N, and the amount of data, D, a principle vividly demonstrated by that groundbreaking chinchilla work.
Right, the N and D square root relationship with compute. Then we saw compelling evidence that progress isn't solely driven by just throwing more raw physical scale, more compute, more data at the problem. Algorithmic improvements, the ones that make compute itself more efficient, are a rapid and incredibly powerful force, contributing roughly equally to the performance gains we've seen over the years.
That compute augmenting progress, having requirements every 9 months potentially. And then we learned that optimizing for inference time is a critical and quite distinct challenge in the scaling picture. We saw that sometimes using a smaller model combined with a sophisticated inference strategy like the rebase search algorithm can actually outperform a much larger model when both are operating under the same fixed inference compute budget.
Getting more out of less at runtime. And finally, we saw how all these diverse principles, the ND balance, the need for massive data and resilient infrastructure, the power of algorithmic innovations like synthetic data for post-training, the cleverness of compositional approaches for multimodality, and the constant grappling with inference efficiency and safety, how they were all integrated and applied in the complex real-world development of a state-of-the-art model family like Llama 3.
And we capped it off by seeing that these scaling phenomena aren't confined to language. They extend to other demanding generative domains like video diffusion, although the specific details, like the critical sensitivity to learning rate and batch size, can differ.
The overall picture that emerges then is that scaling AI effectively isn't a simple matter of just chanting bigger is better. It's a much more complex, multifaceted challenge. It involves this careful balancing act between different resources, actively leveraging algorithmic innovation, optimizing efficiency across the entire life cycle from training through to inference, and crucially, recognizing that the specific rules of this scaling game can change depending on the particular AI task and the architecture you're using.
It really feels like we're only just beginning to properly map out these complex relationships across the vast and rapidly expanding landscape of AI possibilities. As the Llama 3 paper itself acknowledges quite humbly, the field of truly understanding these deep scaling dynamics is still very much in its early stages.
Yeah.
And that's perhaps the most exciting thought to end on, isn't it?
It is, because given the incredible pace of algorithmic advances that we're seeing, the ever-increasing scale of data and compute that's becoming available, and our rapidly improving empirical understanding of these intricate scaling laws that we talked about today, what truly new capabilities and perhaps unforeseen efficiencies might the next generation of AI models unlock?
And maybe more fundamentally, how will those deeper insights into the science of scaling ultimately alter the way we build, deploy, and perhaps even interact with artificial intelligence in the years to come?
That's definitely something to mull over as you continue your own deep dives. Thanks for joining us.